class. So unless you want to interrupt, that's fine, and digress a bit. The plan was to introduce ourselves to Laplace transforms. So the previous 2 weeks have been looking at chapter 2, and assignment 2 melds with that, and so you get a little bit of time just to make sure you put that in, or at least from today's date. So the next chapter, so chapter 3, is Laplace transforms. So if you've done Maths 220 before, then you will have done some of Laplace transforms earlier. So let's talk about revision for the moment. So this is a revision from Maths 220. Now, so the study guide recovers all the stuff from Maths 220 again, with a slight complex analysis bent to it. And so I just want to reformulate it. So if you've got a function, f of t, and we only really care if it's defined for t greater than or equal to 0, and if it's nice, what I mean by nice, I won't write it down, but nice means that if f of t is piecewise continuous and bounded by an exponential, so essentially that's what I mean by nice, then what we can do is we can define a particular transform. So we call it f of s, and it will be the Laplace transform of this function f, and for a particular variable s, and we define it to be the integral from 0 to t of e to the minus st ft to t. That's sort of the definition. So that's the definition of a Laplace transform, so the integral definition, which as a matter of fact we won't use very much actually. So the way most people do Laplace transforms is to use tables, either going forwards or backwards, and indeed that's how Maple does it too, where it can, only falls back to integrals where it has to. So same idea. So that's the definition though. So given a function, which is defined for t greater than or equal to 0, by taking the Laplace transform, you get another function, and where little f is a function of time commonly, or a variable at least it's defined for greater than or equal to 0, then capital F is defined for a new variable s. Broadly speaking, s is some sort of frequency. So s is in general a complex number actually. So it's going from the time domain to frequency domain is how I often describe it. And so you can go backwards too, almost. So you're given a function in the frequency domain, so a function of s, you can go backwards to work out a function which you can take the Laplace transform to get for it. Well, almost. And when I'm over almost is, if you go forwards and backwards again, then the two functions will be equal almost everywhere. And so there might be a slight jumps here and there that might be different, but otherwise it's the same. And so long as you insist on things being continuous, all that problems disappear. And again, physical situations tend to have continual solutions, and so we're quite happy there. So the main application we've got to have in mind is we're going to think of ordinary differential equations. In particular, we're going to look at initial value problems. So in an ordinary differential equation, we know what things are at t equals 0. That's sort of the situation we want to consider. Then when you take the Laplace transform of an ODE, then it ends up being an algebraic equation, or equations as the case may be. So it's basically ordinary differential equations get converted to algebraic ones. Now it works really well if they're linear. So if it's a linear ordinary differential equation, it goes to linear algebraic equations, which we know how to solve quite easily. So just using matrices, invert matrices, etc. And then once you solve the algebraic equations, then we can go back to finding the initial answer. And that's really what that's the main thing we have in mind. So to solve an initial value problem, we'll take Laplace transforms, get our algebraic equations, easier to solve, so therefore solve them directly, then take the inverse Laplace to get the original answer. And that's what we're focused on in this chapter 3, really, is getting the skills to be able to do that. So I would like to do it for second order differential equations, but also systems of linear equations. And again, you've seen that presumably in 220, that's what it is. So the extension parts of it, which we'll get to later, is looking at different sorts of functions. So we're looking at ones which are not continuous. So looking at Laplace and inverse, so Laplace transforms of discontinuous functions, which are useful. And that really helps us to solve more differential equations that way. Looking at things like periodic functions as well. And look at how it fits in with systems of equations, not just simply a 1 second order. Later on, chapter 5 in the subject, we'll also look at how it applies to a partial differential equation. And a partial differential equation is one where it doesn't just have straight derivatives, it also has partial derivatives in it as well. So that's the basic overview. So let's look at some properties. So the Laplace operator is linear, just like integration and differentiation are, which basically means if you've got a Laplace of a sum, it's just the sum of the transforms, that sort of thing. So not much. Then you can work at the Laplace transform of lots of things. So Laplace transform will say e to the at, for example. You can work it out by integrating. So this is one of them. But in truth, there's a table which has them all. So table on, say, page 168 of the study guide has quite a few. And I'll mention more just as we need in today's example. So that's just one, but you can do the table. And instead of having to derive them all self-integration, the table's really the key thing. There are a few useful rules. So the first one, which was introduced in Maths 220, was S shifting. So the first shifting theory. So if you're doing a Laplace transform of any function at all, so ft, so how about just take a step back? So let's just use the convention that, just for short, the Laplace transform of little f will equal big F. So I'll use that convention a lot. It just makes it easier to write down, really. So the Laplace transform of little f is capital F. So the Laplace transform of an exponential times by little f is equal to big F, where the S has been shifted by A. That's the first shifting theorem. Just highlight that. And that's a useful result going both ways. So both taking Laplace transform, so if you get exponential times by sine, for example, then you could use it, or going backwards. So if you've got, if you can see that if you complete the square, you go, oh, I've really got a s minus 1 squared, then you can go backwards as well. So it's useful going forwards and backwards. So it's S shifting. So other ones is, well, at the end of the day, I guess what we have in our mind is, although this is useful to find some Laplace transforms, the main application is derivatives. So I would like to be able to work at the Laplace of a derivative or a double derivative, etc. And roughly speaking, the Laplace of a derivative ends up being multiplication by S. That's roughly what it is. I say roughly because it's almost because you have a minus initial value. So the Laplace transform of a derivative is S times by the Laplace transform of the original function minus the initial value. And you do Laplace transforms of higher order derivatives too. Just a second order probably be all sufficient for us. So double derivative would mean multiplying by s twice, roughly speaking. And then the order, and then you get some initial value stuff cropping up. So these two results, again, are really useful to help convert from a differential equation into an algebraic equation, because it converts derivatives into just multiplication by s, which is a bit easy to deal with. And that's really the heart of doing it. So that works really nicely if things are completely linear, we've got constant coefficients. If the coefficients are not constant, then, well, it can be a bit trickier. But, I mean, some situations still can apply to that. So far, that's the rough summary of what was covered in Maths 220. So hopefully that's all stuff you've seen already. Now, if you don't remember it very well, or maybe you didn't actually cover it, then you'll just need to do a bit more work. And it is all there in study guide. It is self-contained. But they're just sort of the highlights of things that you need to be on top of. And I will use, certainly use these in a second as an application. Let's look at some new stuff. So these are some things, and this is starting from about section 3.67, I think it is, of the study guide. I can't remember what it is. And this first one is called a step function. So first, I'll tell you what it is, give you a sense of what it's useful for, and then talk about the Laplace transform. So using what the textbook is, they call it U. So U of t minus a. I'll draw a picture of it first. So this is so it's defined for time. Give some sort of a here. So pretty much it's at 0 until it gets to a, and then it jumps up to a value of 1 at a. So it's just little dots here. So it steps up or jumps up at a, and the size of the jump is 1, so to speak. So it's stepping up. And so it's 0 if t is less than a, 1 if t is greater than a. And at t equals a, it doesn't really matter what it is in summary capacity. Usually it doesn't make much difference in any application. For our definition, we'll make it 1 at t equals a. But it really doesn't it rarely makes a difference. And when it does, you've got to be more careful with it. So that's pretty much it is. It just sort of jumps up. And so, where would you ever use it? Well, again, in applications, which I'll do in a second, it's like turning things on, right? So basically, before something's off, when any day you turn it on. So like flipping the switch. Or another, you've got a mass at rest. You're just going to leave it. You just leave things as they are, and then all of a sudden you go, let's start these things happening. So if you're modelling an epidemic, maybe the government just lets things going for a while, and when things starts getting bad, that's when I start intervention. And the step function can model when you trigger the intervention to come in. So when you turn it on, you can also use as an idea of an indicator. So an indicator function basically jumps up. Let's make it a bit better. Jumps up between A and B. So basically it's on only for a short period of time. And you can do those. So that would be U t minus A. So it's jumping up at A, and then it's jumping down at B. So you could, by taking differences, step functions, you can, just go, well, I want things to turn on just for a short period of time. So that's sort of where these things are useful for. And so they have other names. This step function is also named after a guy called Heaviside, so it's called a Heaviside function sometimes. So and that's the name that you'll see in Maple if you use that, for example. Okay, so that's what it is. So we would like to be able to use it in modeling of differential equations, and therefore to be able to solve those sort of differential equations, we need to know what the Laplace transform of this is. Let's work out the Laplace transform of just the step function we just used t. That would be where it jumps up just at t equals 0. And that's equal to 1. I'm just being forgetful here, aren't I? Yeah, it's 1 on S. So that looks funny. That's why I had to pause for a sec. If you think let's think what UT is. And this would be the function which jumps up all of a sudden at 0. Now, when it comes to Laplace transforms, if you think back to the definition here, the integral starts at 0. And so what the value of the function is before 0 is completely irrelevant. It doesn't actually affect the Laplace transform whatsoever. So the fact the step function was 0 beforehand, or it could have been anything else, so it could have been 1, doesn't make much difference. So the Laplace transform of the step function at 0 is the same as the Laplace transform of just a 1, which is still 1 on S. And that's why I look funny, because I know what that is. So it really doesn't make a difference. So what would it be in general? So if you did t minus a, where it jumps up a bit later, then it's e to the minus as on S. So you get this e to the minus. So when you shift the step function a bit, so shifting in time, you get an e to the minus as term. And indeed, something that's more useful in general, this is called t shifting. If you do the Laplace transform of the unit step function times by some function, so f of say t minus a, then this is the Laplace transform of the original function times by an exponential. Now I'll use this in a second, give an example of it. So we've already done S shifting, and this is T shifting. So you can see there's some relationship here. So when you shift, when you shift in the time domain by an exponential, it shifts in the frequency domain by just. And so if you just multiply in the time domain by an exponential, it becomes shifting in the S domain. The other way around, if you multiply the frequency domain by an exponential, you end up producing a shift in the T1. And so there's some relationship there. The exponential is the opposite, so this is negative rather than positive, so there's a change in sign there. And because Laplace is based on initial value problems, you're getting the step function comes out to show that indicates an initial value problem. So the step functions are really rise from that. And so there is some correspondence there, but it isn't direct. So where this is all coming from is Laplace transform is really an extension of a Fourier transform. Fourier transforms are nice; they don't have any beginning or end, so to speak. And so there's with Fourier transforms, you can see there's not properties for S shifting, T shifting, those sort of things. And it match up much easier. You can see the connection. With Laplace transforms, which have essentially it's a Laplace model rotated in a complex plane through 90 degrees, getting changes in sign happening and things like that. So you can see connections between it all, but not quite as neat as some other ones. But that's okay. We just learn them and use them. So this is T shifting, and so this basically allows us to take Laplace transform of any function which just turns on all of a sudden. So it could be, and so this U just turns it on essentially. So at T before, when T is less than A, this is 0, when T equals A, bang, it just starts whatever this function is essentially. So that's one thing. Another useful function is called the Dirac's delta function. And I won't say function. It's not really a function, as you'll see in a second. I'll give some properties first, and then I'll draw it. So essentially, it's called D, and again I'll do it T minus A. So if you integrate from 0 up to infinity of this function here, Dirac's delta function, then you get 1. So it's a function that's defined so that the total area of the curve is 1. That's one definition. That's useful to remember. I want to draw the picture of it. Secondly, when T is not A, so everywhere except for the at the point in question, it's 0. So if you're trying to think what is this, let's try to draw a picture of what it looks like. So outside of A, the function is 0. At A itself, it's got to contain a lot of area. It's got to contain a unit of 1 area, all in one little place. So essentially, the Dirac delta function corresponds to a big, massive spike. I can draw the whole thing up. If I can draw a straight line on the screen. So it's a big, massive spike at T equals A, essentially. So it's not a real function, actually. It's you have to use other words, like it's a distribution is the fancy word for it. You can think of it as being a limit of a certain indicator function. And so that's explored in the study guide. So because I want to do other examples, I'll leave it there. So it's basically a sense of, this is the sort of key property. So where is it used? So if you end up in a physical circumstance, say you just give a little bump, just a little push to something. So the Dirac delta corresponds to giving a push with a unit of 1 impulse. So just a gentle push. So if you're doing a sharp push with an impulse of say 10, it then would be 10 times the Dirac delta. That's sort of the idea. So it's just having a quick, very sharp push against of something, and often that might set it in motion, for example. So just a little bump, and the fact that it's been normalized to have area of 1 will give the corresponding units. And so again, when you're trying to think through stuff, so sometimes when you want to model physical circumstances, that's what we're thinking from. If you've got a change happening over a certain time period, you could use an indicator function. You can have it on and off. You can use a step function. If you just want to model something where where there's a very sudden change in the system, you can use Dirac delta's function to try to model that. That corresponds to a very quick, sharp change in the system. So that might be an earth. You could use that for shock analysis. So what happens if there's a big all of a sudden shock in the system? How does it change it? And that's where you can sort of model that way. Okay, so that's the theory that I want to cover today. So the new stuff, just emphasizing that I've put in, really is step function, T shifting, and Dirac deltas. That's the 3 key stuff. Let's see them in some action. So let's do an example. Okay. So just before I do that, how much of this do you remember from 220? Like, do you remember the stuff that I claimed to be revision? Do you remember doing that in 220? Yep. And have you seen step function or Dirac deltas function or anything like that? Yeah. So they all are useful. So let's do a really simple scenario, just to make the things not too complicated. So imagine you've got a weight 10 kilograms hanging off a spring with a stiffness of 40. And then what we're going to do is we're going to apply a force, looks like little f, over various times t, where you're going to bump this mass up and down, so to speak. Now, I haven't damped it, so in a real system it would really be damped. But we'll make it not damped again, just to make the mathematics a bit easier. But the process would be similar if it would be damped, just slightly more complicated formula. So the F equals ma, so that's ma. So is equal, the total acceleration is caused by the force due to the spring constant, which is minus kx, plus the other force applied. And so you quickly get down to this differential equation. So we'll consider this example two different ways. So firstly, let's put some numbers here. So m is 10, k is 40. I've got that already. ft is some sort of force. So let's make it a bit easier on ourselves, that the initial position, initial speed of a mass is 0. Now, normally when that happens, when you have everything's at rest to begin with, it's just going to stay at rest. But we can change it by applying a bit of force. So why don't we just leave it alone for a while, but at t equals pi, let's start moving it. And the way we're going to start moving it is by using the sine function. So pretty much the function ft, the force applied is going to be 0 for a while. So let's try to draw a picture of it. So it's going to be 0 for a while. Then it gets to pi. And then at pi, it's going to look like sine. And sine will stay, because it goes up, would look like this. So that will be with the force. So you can see there's going to be nothing happening for a while, and then all of a sudden at t equals pi, you're going to start pushing down, you can push back up again, and that will move the mass a bit. And then the spring will start causing some other sort of motion happening. So what I want to do is I want to find what the x is as a function of time. And what it is before t equals 0 doesn't really make much difference. What t equals after 0 is important. So initial value problems are really well solved by Laplace transform. That's where Laplace is really good. So let's take Laplace transforms on this, and so we go. So putting all, we've got 10, the double derivative. I could make it x double dot, x double dash, almost the same thing. X double dot I normally use for time, but other than that, that's the only real speciality I would use it for. Or sometimes use it for variety. So what I'm going to do is I want to take the Laplace transform of both sides of this equation. And by taking Laplace transforms, you get an algebraic equation instead. So it's linear, so therefore the 10 just sticks around. So it's the Laplace transform of the double derivative. And like I said before, the double derivative would be s squared times by the original Laplace transform. And again, let's make ourselves easier. Let's do the Laplace transform of x, be capital X. So it'll be s squared x. Well, almost. And I said before, be minus the first derivative at 0 minus s times by the value of the initial function. So that's one of the rules I said I used before. Again, we'll use that quite a lot. They've got plus 40 because it's linear, you can just leave that by alone, and the plus trend for little x becomes capital X. And then we have to write this last term. So let's just rewrite it. So in order to apply this one, when you've got a step function times by another function, we really would like to use t-shifting. Let's roll over here. And you can see with t-shifting, you really need to have u t minus a, well, we've got that sort of thing, what u t minus pi, but the function needs to be also shifted the same amount. So I'm going to have to rewrite it down a bit. So I'm going to have to write it as t minus pi to get the right sort of thing happening. But I can't do that willy-nilly. I do have to, if we're going to subtract pi, I'm going to have to add pi to balance it out. And so in order to work with it, Laplace transform, it's good to simplify it. So sine of t minus pi plus pi, well, if you do sine of something plus pi, it ends up being minus sine. So what this is saying is that the step function of sine t is really the normal sine function being shifted by a minus, so it's really, I've got to make this really clear here, because it's not. It's really minus sine. And if you look at my picture here, you can see this red curve here really looks like minus sine just being shifted away from the origin. And that's what the sense of it is doing. So it's just been minus sine being shifted along by pi. So when I take the Laplace transforms of that, well, the minus 10, because it's linear, just sticks around. And we've got u t minus pi sine of t minus pi. And so what t-shifting says is that would be equal to an exponential e to the minus pi s times by the original Laplace transform. So it'll be e to the minus pi s times by the Laplace transform of the underlying function, which in this case is sine. That's the t-shifting. So, and then to finish it off, to work out the Laplace transform of sine t, what I'll do is just look it up really, and if you look it up, it's 1 over s squared plus 1. So I've just looked that up really, is what it comes down to. So any questions with that? So you can see I've used the rules for Laplace transform of double derivative, and I've used t-shifting, and I've looked at the Laplace transform of a sine. So putting it all together. Next you want to solve it all. And so something's nice, that's 0. That's 0. So they just disappear. What else can we do? So we can divide everything by 10. That makes things look a bit easier. So on this side, you end up getting s squared plus 4 outside of x is equal to this side here. And so therefore x must be equal to minus pi s and s squared plus 4 s squared plus 1. And so what we've done is, differential equation, well, not quite clear how to solve. So certainly when you've got step functions. So when you've got a step function, it's annoying to solve it the ways we've normally done it. And the reason is because you've got to consider 2 different pieces. So you've got to work out, so the way to do it, the method you've done it before is, first I'd solve it for t less than pi, like your normal way, which is not that hard actually. And then you solve it a new separate case for t at equals pi. So for t greater than pi. And so you'd have to do it in two different pieces. That's how you do it in the traditional way of doing it. Laplace transform does it all in one go. That's the beauty of it all. And so it basically convert the difference equation into an algebraic one, which was pretty easy to solve. Just divide by size by s squared plus 4. So now what we need to do is just take the inverse Laplace transforms, and bang, that's the answer. Easier said than done, unfortunately. But still got to work out the inverse Laplace of this one. Now, you can use the tables. So the e to the minus pi s on top. In order to use that sort of stuff, we're going to have to do some sort of that sort of presence is going to give you t shifting and cropping up. So that's all right. We'll handle it in the case. So if we can just work out the inverse Laplace transform of everything else, then we can use t shifting to work out the final answer. These exponentials present. So it's really just thinking about as 1 on s squared plus 4 on s squared plus 1. If we can work out an inverse Laplace transform of that one, then we're hunky-dory. The issue with that is, so it's really about, so the way to do these things normally is using partial fractions. So I'm going to do that here. So I really want to write this down as, split up into its two different functions. Just going to work them out. So in general, would be, there's no odd terms at the top. So it's really just, you can do it in terms of just s squared. So a polynomial s squared. So you could just be a on s squared plus 1 plus b on s squared plus 4. Use partial fractions to simplify it. This case is pretty simple, fortunately. It's just going to be 1 on top. So you get 1 on top, the s squared's got to cancel out. So I would just do 1 minus 1. Would work pretty quickly. So just try it out and see how I go, how close I am. So you do s squared plus 4 minus s squared plus 1. Doesn't give you 1, it gives you 3. And so if I divide both sides by 3, then it works. So I've done partial fraction decomposition a bit more of an ad hoc fashion. Works for simple cases, not in general, but it works in lots of cases still. So let's just clean it up. Let's put the third out, put the minus sign in. So now we've got to try to, so the 1/3 linear, we can worry about at the very end bit. The e to minus s would do some t shifting. So we just need to work out the inverse Laplace transform from these two functions here. And these are close to what's in the table. So if you put a 2 on the top, you have to multiply it by half for it to work, then this is one of the different things from the table. So do you know what the inverse Laplace transform of 2 on s squared plus 4 is, by any chance? Okay. If you can find in the table, so page 168, I think it is, of the study guide. So when you got a constant on top of s squared plus something or other, ends up being some sort of sign. So I think you get sine 2t, and 1 on s squared plus 1. We did it earlier actually. That just gives you sine. Now I've got to make it clear here. That's the Laplace transform of it. Or maybe putting it more clearly. So it's 1/3. Just so I know. So it's clear what I'm doing for the next step. The Laplace transform of half. Sine 2t minus sine t. So when you've got an exponential like this at the front, the way to do it is just work at the inverse Laplace transform of the rest of it. That's what I've done here. And then use t shifting. So let's just put the result down. So if you've got the Laplace transform of u t minus a f t minus a, that's equal to e to the minus as of the Laplace transform of f at s. So that's what it pretty much says. So let's think how it matches. How things match up. So we've got the pi and the a. So the a is just going to be pi in this circumstance, and the function f, which we want, is going to be this thing here. So see how they match up. So therefore, if you take the inverse Laplace transform of capital X, which we're just going to call little x, which is what we're trying to solve in the first place, is going to be the 1/3. That's just sticking around because of linearity, and then otherwise we've got the exponential Laplace transform function. So it's going to be u of t minus pi. So you can see I'm just plugging this bit in. So u t minus pi, and then the function I've got up here. So half of sine. And instead of writing just 2t, I'm going to write 2t minus a. And a in this case is pi, so t minus pi. And if you expand it, 2t minus 2 pi, as a matter of fact. And then same with minus sine. So writing the sine t, I'm writing down t minus pi. And that's the answer. It's really worthwhile simplifying it down a bit. So let's give it a go at that. So sine 2t minus 2 pi is just going to give you a half sine 2t, and we might as well bring the third in, so it's going to be 1/6 sine 2t. Sine of t minus pi gives you minus sine, so minus minus be positive, so positive 1/3 sine t. And again, if you can write it down, this is a step function, so it turns it on. So basically, if t is less than pi, it's nothing. And so and otherwise, so when you get t is greater or equal to pi for that matter, we're getting this function here. That's our answer. So if you think back in terms of the original thing, so we've got our little mass up the top here, all the way at the top. If we're bumping it, so if we at t equals, say, we don't do anything with it, so just leave it alone for up to pi, which is why nothing's happening. So x is 0. But at that point in time, we start bumping it. We start bumping in this sort of red curve here. That's given by a sine function. So you can see what happens is that after t equals pi, then you're getting the impulse you're giving it to it. So the force you're applying to it results in movement in the same sort of way. So you're getting a sine t term, matches up to the input frequency. So the input frequencies and the output frequency match up. So they're both the same sort of frequency for the sines. But you're also getting an extra term, so 1/6 sine 2t, and that corresponds to the natural frequency of this particular problem. So that's some sort of resonance happening. So in a real life situation, you'll also have damping, and so things would, any motion you apply to it would decay that way, and so other bits would start decaying off, and really only the resonant frequency would really come strongly, and so you get some sort of resonance happening. or so long as the input frequency is close enough to get the resonance thing happening. If it wasn't, then they'd all just decay. You wouldn't get much happening at all. So that's one application of you showing you how the step function can be used in a physical circumstance. So just starting to do movement and how you sort of solve it and how you can use the inverse Laplace transforms of those. So I'm looking at T-shifting, both doing Laplace and inverse Laplace, and how you can use it and how you can actually use it in an application. So second example, which it was all I have time for doing, let's start at 10, so with no velocity, and so if you think about it, what it is, so let's just make it, won't worry about FT for the moment. So if you started this thing, this is your little mass. So essentially what we've done is we've just pushed it up, pushed up the spring a bit, and it's going to let it go. And if you think about it, it's just going to, because it's on the spring, it's going to bobble up and down. And because there's no damping, it'll just bobble up and down forever. So nice simple harmonic motion. So it's going to bobbling up and down. What happens if we leave it at for the moment, but then when you hit at t equals pi, we just bump it and give an impulse floor of 20. So that's basically applying a very quick sharp force. So the 20 just shows that's the magnitude of the impulse, and at t equals pi. So what happens if you just do a bit of a shove? How does the motion get changed? Essentially what's happening. And again, you could do this by by mechanisms already done, by solving it first for t is less than pi, and then the impulse here will change the velocity. So the impulse is the change momentum, and then you can use that to work out what the change velocity is. The position won't change; it's just instantly, but it will change the speed, and you can therefore solve a new initial value problem. That's sort of a more direct way of doing it. But Laplace transforms do it nicely. And so back to terms of differential equations. So if we have everything else it was before, so we had 10 times by the first double derivative plus 40 times by x is equal to this thing over here, so 20 Dirac delta minus pi. So if you take Laplace transforms of both sides, so much like we did before, so I'll have 10 s, like a capital X squared even, minus s x dash minus x. And this is what I forget this sometimes. It's the other way around. So it should be x dash there, s x naught, s x. Plus 40, and when you Laplace transform to little x becomes capital X, Laplace transform of Dirac delta. Now I should have told you what it was. I should tell you here now. So the Laplace transform of the Dirac delta is just e to the minus as. So it's really just one, so to speak, shifted along. So it's again, there's some c shifting going along. So the Laplace transform of the Dirac delta by itself is just one. And so the Laplace transform of 1 was 1 on s. Dirac delta of t is 1 on s squared, that sort of thing. So it's sort of one up from that. So therefore, just doing all that, so the Dirac delta would be e to the minus pi s. Then we sort of solved as before. So that was 0. That's equal to 10. Let's not make it. Let's make that 1. Let's make it easy on ourselves. Sorry, changed my mind here too much. So cancel out all the 10s out. And so we're getting s squared plus 4x minus s, so just those terms, is equal to 2e to the minus pi s. So put the s on the other side. So capital X would be s plus 2e to the minus pi s. And then divide both sides by s squared plus 4. So what I've done, big picture, it's a good thing in terms of strategy here, is I've got a differential equation involving discontinuous function, which is an initial value problem. Laplace transforms is a really good way of doing that. So to do that, I've taken Laplace transforms, remember all my rules for derivatives and the impulse function on the right-hand side here. That produces an algebraic equation in S. I've solved it. So it took, it looks like one line to solve it. Then, so take Laplace transforms, solve algebraic equation, then take inverse Laplace transform. And so in order to solve it, again, I just want to really split it up. So I've got a S on s squared plus 4 here, plus e to the minus pi s, 2 on s squared plus 4. And I want to take the inverse Laplace transforms of both sides, really. So, and it's the best way to do it term by term. So s on s squared plus 4, again, if you look up the tables, have you got the tables in front of you? Do you know what the inverse Laplace transform of s on s squared plus 4 is? Yeah. So that would be the Laplace transform of cos 2t. Now, I haven't run inverse Laplace transform on one side, because I want to do it a little bit at a time. So you got e to the minus pi s. So the inverse Laplace transform of 2 on s squared plus 4 is? Can you tell me what to type it in? I thought it was sine 2t. There's a 2 on the top. Yeah. So, I mean, because there's a 2, that already takes into account. So it might be written in, actually, a Laplace transform. And so when we do the so that's fine. When you've got an exponential times by a Laplace transform, when you bury that in, so to speak, it does a t shift. This is the t shifting cropping up. So it'd be shifting the whole thing by what a value is at the top here. So I shift it by minus s. Sine 2t, again, shifted by pi. And then got minus, doubling, it's 2 pi. And therefore, the inverse Laplace transform of x, which is our function we really want to find out in the end here, is therefore equal to cos t, cos 2t even, plus u t minus pi times by, well, sine of minus 2 pi, well, it's periodic 2 pi, so just sine 2t. And again, you can write that down as piecewise if you wanted to. We'll just see what's happening. So when t is less than pi, this step function here is just 0, so just getting cos 2t. When t is greater than pi, so t equals pi, just bumping it all of a sudden, then the underlying dynamics stays the same, but you're just adding to it. The bump just adds on a sine 2t. And if you think about it, if you put these together, so sine 2t plus cos 2t plus sine 2t. If you wanted to, that's equal to root 2 sine 2t plus pi and 4. Got to write it as a 1 sine. So if you think about it, just useful to think some stuff. So initially, the math is sort of bobbing up and down in nice product fashion, so cos 2t. Then you bump it. It's a big bump happening. But as a matter of fact, I've wriggled a lot here, but you're bumping it. It's really bad drawing. So it's starting at cos, so it's actually going like this. So you're bumping it after one period, actually. So that's what it is. That's what you're doing. And then you bump it all of a sudden, and it starts. Now, when you bump it, it now becomes an amplitude of bigger. So it's, instead of amplitude of 1, it becomes an amplitude of root 2, but it still keeps the same sort of frequency. So I'm not really looking at what's happening, but it's going to be that nice regular pattern, but instead of just that, but it's going to have a bigger amplitude. So you can see by bumping it, you've increased the amplitude. Change the phase slightly, but the key thing is increase the amplitude, but the frequency stayed the same in this particular case. So both these examples are undamped, and so if you've got damped, which is more realistic, then you get some sort of different sort of behaviors happening. But it does show you both mathematically and also a bit more conceptually how this Dirac delta functions are happening. So you can see that it's just going normally. You just bump it and it changes the motion. In this case, you're actually making the oscillations bigger, essentially. So any questions with what I've done? Okay. So just in summary, just remind what Laplace transforms were, and then introduced the step function, Dirac's delta, and t-shifting, and just should have shown you how they apply to differential equations. And again, as I said, you can actually have done those without Laplace transforms, but Laplace transforms make it really neat. So Laplace transforms is particularly really nice when you've got initial value problems, in particular when you've got discontinuous functions cropping up, like these ones here. So Dirac delta, step, fantastic for those sort of stuff. But they're useful in other circumstances too. So they're useful even if the Dirac or is continuous. So that's it. So next week, there'll be more Laplace transforms.